In the previous video, we defined the adjoint of a differential operator, and we did this by showing that it's analogous to determining the transpose of a matrix A in linear algebra. Now you remember from earlier considerations, if you have a symmetric matrix with distinct eigenvalues, the corresponding eigenvectors can be proven to be mutually orthogonal. So what we're doing here, and this started in the previous video, is to determine the analogous requirement for a differential operator to have mutually orthogonal eigenfunctions. So we started in the last video by defining the adjoint of a differential operator, again by analogy to the transpose of a matrix. And now we want to look at what is the requirement for such a differential operator in order for it to have mutually orthogonal eigenfunctions. So just like a matrix is symmetric if A and A transpose are the same, we're going to say that a differential operator is self-adjoint if L and L star are the same. Some people use the more general term Hermitian, which applies also in the complex case for linear algebra, but I'm going to use the term symmetric in the linear algebra matrix context and self-adjoint in the differential operator context. So let's prove that if L and L star are the same, so that the differential operator is self-adjoint, the adjoint is the same as the original operator, let's prove that the eigenfunctions must be mutually orthogonal. And let's take U and V to be two eigenfunctions of that differential operator. U is the eigenfunction that corresponds to the first eigenvalue lambda 1, and V is the eigenfunction that corresponds to the second eigenvalue lambda 2. So let's start with that original definition for the adjoint. It was the inner product of U with LV is equal to the inner product of V with L star U. But now L and L star are the same, so we can just replace the adjoint with the original differential operator L. You remember in that context, in the previous video, U and V were just generic arbitrary functions. Now they are two of the eigenfunctions of our differential operator L. So because of that, L operating on V, well, that's just lambda 2 times V. So we can replace that here. Likewise, L operating on U, well, from this eigenproblem, that's just lambda 1 times U. So we can replace that here. Now lambda 1 and lambda 2 are scalars, so they can just come out of the inner product. So on the left we have lambda 2 times the inner product of U with V, and on the right we have lambda 1 times the inner product of V with U. Remember, the order of the functions, just like with vectors, doesn't matter within the inner product. So let's bring both of these to the left-hand side. So then we have the quantity lambda 1 minus lambda 2 times this inner product of U with V must be equal to 0. That follows directly from here. So what happens is, just like in the matrix case, if the two eigenvalues are distinct, then lambda 1 minus lambda 2 will not be 0, so that the only way that this product can be 0 is if this inner product U with V is equal to 0. If the inner product of two functions, just like vectors, is equal to 0, then that means they are mutually orthogonal to each other. Now in the vector case, that has a geometric interpretation. They're mutually orthogonal, they're perpendicular to each other. That's not the case here, but we still call them orthogonal. All right, so we've just shown that if L and L star are the same, so if our differential operator is self-adjoint, and the eigenvalues are distinct, then the eigenfunctions are mutually orthogonal. Very similar to the linear algebra context that we looked at earlier. Now clearly not all differential operators are self-adjoint. We did an example at the end of the previous video where that was the case. We had L, we got the adjoint operator L star, and it was not the same as the original L. So not all differential operators are self-adjoint. So what we'd like to do is come up with a requirement. How can we test for whether a differential operator is indeed self-adjoint and therefore has mutually orthogonal eigenfunctions? So we're going to again look at this general second order linear variable coefficient case that we looked at in the previous video. This is a very common case in applications, and we'll build on the results that we had in the last video. So if you remember there, the adjoint operator L star operating on V, that was 1 over the weight function W times the second derivative of A0 times V minus the first derivative of A1 times V plus A2 times V. Remember, the variable coefficients went inside the derivatives, and odd order derivatives change sign because of the integration by parts that's necessary to get the adjoint of a differential operator. Okay, so this is the general result from the previous video, and you should take a look at that if you have not already. So let's expand out these derivatives. Let's use the product rules on these, and I've color-coded them so you can see where all the terms come from. So the product rule on the derivative of A1 times V, Well, that gives you this term and this term. This product rule here with the second derivative gives us these three terms. And I've grouped the terms together. So this is everything times v double prime, this is everything times v prime, and this is everything times v. And what we'd like to do is take a look at these coefficients on each of those three terms, v, v prime, and v double prime, compare them to the corresponding general form of the original second-order linear differential operator with variable coefficients, and see what has to be true about these coefficients in order for their operator to be self-adjoint such that L and L star are the same. So A0 has to be the same as the second derivative coefficient in the original differential operator, which was also A0. So that's taken care of. Then this one, 2A0 prime minus A1, has to be the same as the coefficient in the original differential equation, which was A1. So let's take a look at that. So we have A1 is equal to 2 times A0 prime minus A1. Well, if you bring this A1 over, then you have two of those, the 2's cancel, and you have that A1 is equal to A0 prime. So there's a relationship between A0 and A1 that has to hold in order for the operator to be self-adjoint. Now let's take a look at the coefficient of the v term. So we have A0 double prime minus A1 prime plus A2, and that has to be equal to the coefficient in the original differential operator, which was A2. So we have A2 is equal to A0 double prime minus A1 prime plus A2. Well, we've already determined that A1 has to be equal to A0 prime. If you substitute that into here, you'll find that this is identically satisfied. In other words, if this is true, then it takes care of the second term as well as the third term. So this is the only requirement between these variable coefficients that has to hold for L and L star to be the same, and therefore L to be a self-adjoint operator. So let's replace A1 in the original differential operator with A0 prime as required by this equation. So then we have A0 u double prime plus A0 prime times u prime plus A2 times u. Now these two terms, it may not be obvious, but it turns out if you do a reverse product rule, you can combine these two terms into one. So when you do that, it gives us this. It gives d dx of A0 times d dx. So to see that reverse product rule, just take d dx of A0 times d dx, and you'll get back to this, of course, when you have it operating on u. So we have 1 over w times d dx of A0 d dx plus A2. If the original differential operator can be written in this form, then it is a self-adjoint operator, and we call that a Sturm-Liouville differential operator. Now, this is not Louisville, it's not the town in Kentucky. It's a smart French guy's name, so it's probably Louville. So Sturm-Liouville differential operator. A second-order linear differential operator of that general form that we had, remember second-order linear with variable coefficients, is self-adjoint if and only if it is of this Sturm-Liouville form, which is written here again. Now you notice I've just traded out the A0 for P and A2 for Q. This is using the general notation that we use for SL or Sturm-Liouville equations. Now the P has to be positive across the entire domain, as well as the weight function W also has to be positive across the entire domain. Now the reason why we give this equation a name is because, number one, it's so common in many, many applications, but number two, because it has this mathematical property that the eigenfunctions of a Sturm-Liouville differential operator are always mutually orthogonal. And it also turns out that any equation of this form, second-order linear variable coefficients, can be put into a Sturm-Liouville form. It may not be in Sturm-Liouville form originally, but we can put it into such a form such that it is self-adjoint and the corresponding eigenfunctions are mutually orthogonal, have all these wonderful properties, and we can use them in that fashion. This also comes up in variational methods. We'll see it in functionals with integral constraints, in the Rayleigh-Ritz method, stability of continuous systems, control of continuous systems, and so forth. So this is a very important result and has widespread applications in the eigenfunction approach that we're using here, as well as in variational methods in a number of other contexts.